We've talked about the ocean a little bit under, for example, geoengineering in terms of how oceans can be used to sequester additional carbon with iron fertilization, with enhanced alkalinity and marine ecosystems and so on and so forth. I'm going to make another podcast looking more at oceans potential for climate mitigation from a nice report that came out of this oceanpanel.org. Just look at the things. There are lots of details in the report. I'm going to just do an executive summary of it as usual. So they are divided into a number of themes of oceans, so transportation, ocean energy, ocean carbon, ocean food, and what else is there, and so on. So you have here ocean-based mitigation options explored in this report and associated annual mitigation potential in 2050. So international shipping can save 0.75 to 1.5 gigaton CO2 equivalent. We will see a bit more about that. Aquaculture can put away 0.04 gigaton CO2 equivalent if it's above zero. Offshore wind can give us a saving of 0.65 to 3.5 gigaton CO2 equivalent. Domestic shipping, seaweed farming, ocean energy, wild capture fisheries, and we have seagrasses. We will address this a little bit. Seabed storage of carbon has a potential for 0.5 to 2 gigaton CO2. Dietary shifts can provide a saving of 0.3 to 1.06 gigaton CO2 equivalent, and salt marshes can put away 0.05 to 0.1 gigaton CO2 equivalent. So ocean covers 70% of the Earth's surface, so obviously if that can serve, already it is taking up more than 93% of the additional energy and 25% of the carbon. Now we are talking about additional mitigation via carbon sequestration and other approaches. So here is a summary of global mitigation potential offered by each area of ocean-based climate action. Ocean-based renewable energy by 2030 and 2050, so 0.18 to 0.25, 0.76 to 5.4. I won't read the numbers in each case, but you should just look at the areas where ocean provides pathways for mitigation. Ocean-based transport, coastal and marine ecosystems, fisheries, aquaculture and dietary shifts, carbon storage in the seabed. Action in this area requires further research prior to implementation at scale. So we don't know exactly what are the remaining knowledge gaps, so we will look at a table to see what are the short and medium time scale research and policy actions needed for each of these things. So in total percentage contribution to closing emissions gap to the 1.5 degree C pathway by 2030 would be 4 to 12%. We will look at a figure next. By 2050 it would be 6 to 21% of the emissions gap. For the 2 degree C pathway it would be 7 to 19% because you have room for emitting more carbon under 2 degree C pathway, and it would be 7 to 25% by 2050. So you can see that the increase is not as large as in the 1.5 degree C pathway in terms of the amount of carbon ocean would have to take up for reaching those goals and reducing the emissions gap. Okay, so contribution of ocean-based mitigation options to closing emissions gaps, again looking at gigaton CO2 equivalent starting here in 2015. The current policy line baseline would take us here. So the emissions gaps to 1.5 and 2 degrees C are shown in terms of the remaining gaps to stay within 2C to stay within 1.5C, and the proportion of emissions gap that could be closed by ocean mitigation in this case is 25%. In this case it is 21%, so it is fairly substantial in terms of ocean's contribution to emissions gap reductions. The contribution of 5 ocean-based climate action areas to mitigate climate change in 2030 as a maximum gigaton CO2 equivalent, so maximum annual emissions reductions. Ocean-based renewable energy, add to that ocean-based transport contribution, coastal and marine ecosystem contribution, fisheries, aquaculture and dietary shift contribution, and carbon seabed storage, remembering that this still requires some research. You would get a total of 3.5 gigaton CO2 equivalent per year, which is 12% of the 1.5 degree C pathway, as we said, by 2030. You do the same thing for the by 2050 for the 1.5 degree C. You would have much more in the renewable energy, ocean-based transport, coastal and marine ecosystems, fisheries, aquaculture, and dietary shifts, carbon storage, together 11.8, so that is 21% by 2050 in terms of maximum gigaton CO2 equivalent needed. Annual greenhouse gas emissions reductions by 2050 is 56 gigaton CO2 equivalent. Out of that, 11.8 could come from the ocean if we did it right. Potential of ocean-based climate action to contribute to current policy for closing emissions gap in 2030. So this is annual emissions gigaton CO2 equivalent. Current policy 1.5, 2.C pathways, gaps for each of the targets, total greenhouse gas mitigated minimum and maximum, percentage gap closed for 1.5 and 2 degree C targets. So today, by 2030 and by 2050 in the current policy, in the 1.5 degree C pathway, 2 degree C pathway, and the gaps, corresponding gaps, total GHG mitigated by the ocean, gap closed 6 and 21. By 2050 it would be 7 and 25. So it's just repeating this figure again. There will be many wider impacts of ocean-based interventions to on sustainable development dimensions. You may have heard that there is a sustainable development goal under the UN, which range from poverty reduction, good lord, I cannot even read it, they're all too small, but they include education, access to water, gender equality, access to energy, food, etc., etc. So unfortunately you'll have to read on your own. Okay, so ocean-based renewable energy, they all map onto, in terms of economy, environment, society and governance, they all map onto these various SDGs, and you can see the given SDG number, and then the impact score is colored as low to high. In the positive case it's the greenish colors. In the negative impact score they are reddish to yellowish colors, going from high to low, low to high. Okay, so ocean-based transport, coastal and marine ecosystems, fisheries, aquaculture, dietary shifts, and carbon storage. So you can see that some of them have significant negative impacts on some of these SDGs. So obviously when you want to optimize just carbon mitigation and drawdown versus other broader impacts, then you have to worry about the impacts on things like the sustainable development goals as well. Moving on, short and medium term policy, research, technology priorities necessary to deliver on mitigation potential of ocean-based climate actions. There are lots of words here I won't read, but they are split into short-term priorities 2020 to 2030, 2023, we're already in end of 2021, so already we are well into the short term. Medium term goes from 2023 to 2025. So ocean-based energy, there are things like undertake marine spatial planning, which would require research and understanding the impacts, positive and negative, of both fixed and floating offshore installations on marine biodiversity. And technology would be to advance storage capacity and design, because bringing offshore energy to onshore use would be very expensive. That would require very deep thinking as well in terms of technology, research and policies. And you can imagine that if you have hard structures putting windmills offshore, and climate change makes the winds weaken or die down in some place, then you have made massive investments on immovable assets, whereas if they are floating offshore wind installations, maybe they can be dragged to a place where wind is still a potential source of energy. Medium-term priorities include things like developing strategic national roadmaps for zero carbon economy in 2050, which would require understanding the potential benefits of co-location with other ocean-based industries like desalination plants and aquaculture. And technology would include advanced technology that can move technologies into deeper water sites. For example, development of floating offshore wind technologies to open access to larger areas of energy resources. Ocean-based transport. Again, there are short-term and medium-term priorities in policy, research, and technology. Coastal and marine ecosystems have short and medium term priorities in policy, research and technology. You can get the report and go through these, because in this short podcast I wouldn't want to read all of them, but you can see what you would expect. Protect coral reefs as important, and integrated coastal defense systems for ensuring the protection of coastal blue carbon system, which is carbon stored into water. And you would need to understand the impacts of climate change on rates of carbon capture and storage, or the potential for restoration. Technologies would include advanced biorefining techniques, allowing sequential extraction of seaweed products. Fisheries, aquaculture and dietary shifts have similar priorities, including eliminating harmful fisheries subsidies, which comes under Sustainable Development Goal 14.6. Develop disaggregated global data sets for greenhouse gas emissions from wild catch fisheries and marine aquaculture, so that in net zero you can also include calculations of those contributions. Extend surveillance technologies for tracking fishing on the ocean and along coastal areas, so monitoring, verification and reporting on these areas can be managed. Seabed carbon storage in short term and medium term would require investing in pilot projects to further explore potential environmental impacts and incentivizing public and private partnerships. Research would go into mapping global geophysical potential with technology on few major technical advances required, as seabed storage is already deployed at international scale, at industrial scale. So how to scale it up is a key short-term priority. In the medium term, develop national strategies and targets. Research would be understanding the impacts of long-term storage on marine ecosystems, and technologies would be needed to scale up in ways that are economically feasible while remaining net neutral or net negative. So schematically speaking, carbon cycle in the coastal and marine ecosystem, if the carbon marine ecosystem is intact, then it should sequester carbon, so it's a net greenhouse gas sink. But if it is a degraded and converted ecosystem, like lost salt marshes or degraded mangrove systems and so on, they would be emitting carbon dioxide, methane, nitrous oxide and so on. So human activities like degradation, impoundment and conversion are leading to additional source of CO2 or the sink is being reduced, being weakened. Okay, so human activities on restoration can resume CO2 sequestration and avoid CO2 emission, methane and N2O emission as well. Okay, so comparison of conservation and restoration pathways for coastal and marine ecosystem. Under conservation, areas converted annually as thousands of kilometers squared per year for mangroves, salt marshes and seagrasses, with the reddish orange colors being low and the yellowish colors being high in terms of conservation. Avoided emissions from mangroves, salt marshes and seagrasses. You can see it's fairly significant in gigaton CO2 per year. This is for restoration, areas restored annually in thousands of kilometers squared per year. So conservation and restoration are different. I hope you understand that. Conservation is you are protecting what is there. Restoration is you are recovering what has been lost. Mangroves, salt marshes and seagrasses, again in terms of area and in terms of CO2 sequestration. Mangroves, salt marshes and seagrasses have these gigaton CO2 per year. What is interesting is we will see how it compares to what we do on land. Mitigation potential for per unit area of restoring land-based and marine ecosystems. Reforestation would give you about 1.5 tons CO2 per square kilometer. Natural forest management would be in the range of 0.1. Improved plantation about 0.2. Peatland restoration is good at 1.8 or so, but mangrove restoration is a whopping 3.1 or so, much larger than reforestation and land recovery systems. Salt marsh restoration is very high. Seagrass restoration is relatively high as well. Coastal wetlands restoring all would give you also 1.7 or so here. So marine ecosystems are safe, as we have said before. It also makes sense that marine ecosystems don't burn down marine aquatic forests like the terrestrial forests do. So more sequestration and longer sequestration as well, because of these resilience to disturbances and lack of wildfire. But of course we have now marine heat waves, and we still don't know how marine heat waves will affect carbon sequestration and marine ecosystems and their ability to avoid emissions and sequester carbon and so on. So obviously those are areas where more research would be needed as well.